So in this video we're going to start talking about chemical kinetics. So what is kinetics? Kinetics is a study of reaction rates, changes in concentration over time. In other words, how fast does a reaction occur? Okay. So what sorts of things influence your reaction rate? How fast the reaction occurs. First of all is concentration. Okay, reaction rates are higher at higher concentration, right? Because this makes sense, right? The more concentrated we make it, the higher the reaction occurs. If we cram more and more of our reactant into the same space, of course the reaction is going to go faster. Okay, physical state. Typically, increasing the surface area will increase your reaction rate. This is a classic example of this that you can do that illustrates this. For example, that if you heat up an iron nail, for example, in an atmosphere of pure oxygen, it will just glow. If you heat it up and dunk it into a bottle of pure oxygen, it'll just glow. If you do the same thing with steel wool, the steel wool bursts into flame. What's the difference there is the surface area. And then the last thing that can influence your reaction rate is temperature. Usually increasing the temperature increases the reaction rate. All right? So reaction rate depends upon concentration. That was one of the things that we just listed that influences reaction rate. So the problem is that the reactant concentrations decrease as the reaction proceeds. Okay, so the reaction rate is not constant. Most of the time, a reaction is going to start out fast when the reactant concentrations are highest, and the rate is going to start to taper off as the reactant concentrations drop. So the rate decreases over time. I think this is something students have a hard time getting their minds around, is that most of the time you're not dealing with something that's happening at a constant rate. Okay, so if a reaction, let's say a reaction starts out fast and then begins to slow down, your rate depends upon the time interval that you choose. Okay, now the initial rate, what we call the initial rate, is the rate at the moment the reactants are first mixed. Okay. The instantaneous rate is the rate at some moment in time, and the average rate is a rate over a specified time period. The problem with the average rate is it depends upon the time interval chosen. The average rate will depend upon the time interval chosen. All right. So let's look at some data. So let's suppose that you are looking at the ozonolysis of ethylene, okay? The reaction between ozone and ethylene. And we measure the concentration of O3 versus time. O3 is ozone versus time in 10-second intervals. And our concentration starts out at 3.2 to the minus fifth. Then it drops down to 2.4. to 1.95 to 1.63 and so forth. Now, can you look at this data and see that it's not going at a constant rate? So in other words, if you graph concentration, and brackets usually mean concentration. So if you plot concentration versus time, it's not going to look like that. It's not going to be a straight line. Well, how can you see that? For it to be a straight line, the intervals have to be the same. In other words, 0 to 10 and 10 to 20 and 20 to 30. That's a constant interval. That's 10-second intervals. But these intervals are not the same. The difference between 3.2 and 2.4 is bigger than the distance between 2.42 and 1.95. In other words, as we go down, the reaction is slowing down. The differences between the numbers are slowing down. If you were to graph concentration versus time, it would not be this nice straight line. It would look more like this, because the reaction is starting out fast and slowing down. But the whole point here, though, for this slide is that the average rate depends on the time interval taken. Okay, so if you do the average rate over the whole period, you do the change in concentration over change in time. Okay, so again, this pops up again. Change is always final minus initial. So our finally we had 1.1 to the minus fifth moles, and we started with 3.2, so it's 1.1 minus 3.2 to the minus fifth over 60, which gives us a negative number, but the negative number indicates that the concentration is decreasing. So this comes out to be minus 3.5 to the minus 7 moles per liter per second. If we do the average for the first 10 seconds, then we just do the difference between these numbers and divide by 10. And that's a much bigger number. That comes out to be minus 7.8 times 10 to the minus 7 moles per liter per second. Okay? And so that's almost twice the number. If we do it for the last 10 seconds, and we take the difference between these two and divide it by 10, and you get 1.3 times 10 to the minus 7 moles per liter per second. Right? So the reaction is starting out fast and then tapering off. So if we take a general reaction, A plus B makes C plus D, the capital letters would represent formulas, and the lowercase letters would represent the balancing coefficients in the equation. Then your rate of reaction, it turns out, is going to be equal to some constant K times the concentration of A raised to some power times the concentration of B raised to some power. Okay, K is the rate constant for the reaction, and this is specific for a given reaction at a given temperature, and M and N are the reaction orders with respect to each reactant. So M and N are the reaction orders. So what does this mean? If M or N is 0, we have what's called a zero order reaction. And changing the concentration has no influence upon reaction rate. I know what we said earlier, just a few slides ago, that as the concentration drops, the rate slows down. But it is possible to have a zero order reaction. Okay, we'll get to why that is much later, but changing the concentration has no influence if the order is 0, because anything to the zero power is 1, so that basically drops out of the rate law. Okay. Now, if M or N is first order, okay, that means that the rate is proportional to the concentration to the first power, which is anything to the first power is the number itself. So doubling the concentration would double the rate, tripling the concentration would triple the rate, and so forth. Okay? Now, if the order is 2 for a particular reactant, in other words, if M or N is equal to 2, then we would have what's called a second order reaction. Okay, it's where the rate is proportional to the concentration raised to the second power. It's a square. So if the reactant concentration is doubled, the rate increases by 4. Okay, and if the reactant concentration is tripled, then the rate increases by 9. Right, because 3 plus 3 squared is 9. But very important down here in bold face font, the reaction orders must be determined experimentally. They do not come from the balanced equation. Okay, they do not come from the balanced equation. This has to be done experimentally. Why that is, we'll see later. Why that is, it's because the reaction might occur in multiple steps, but we'll explain that much later. All right, so how do we do this? How would we determine those reaction orders for a reaction? You have to do what's called the method of initial rates. Okay, that is, how does this work? So what you do is you run the reaction with different starting concentrations, and you measure the initial rate of reaction, and you experimentally determine this. Okay, so if I change this concentration and there's no change in rate, it's zero order. If I double the concentration and I double the rate, it's first order, and so on. So let's look at some data. Okay, so for the oxidation of NO, nitrogen oxide, nitric oxide to form nitrogen dioxide. Okay, so basically, let's suppose we studied this reaction. We went in and we measured concentrations of O2 and NO, okay, and we looked at the rate of formation of NO2. Okay, so in our first run, our concentrations were both concentrations were 0.0010, and our rate was 7.1 moles per liter per second. Okay, if we upped the O2 concentration to 0.004, the rate goes up to 28.4, and if we keep O2 at 0.004, and we increase NO to 0.003, okay, then the rate goes up to 255.6. So how do we figure out the reaction order? So in other words, we know that the rate is going to be proportional to some constant K times the concentration of NO raised to some power times the concentration of O2. I'm just calling them X and Y here. You call them M and N. It doesn't matter. So we have to figure out what those exponents are. Now, so basically we're going to compare, but there's more than one reactant involved here. There's both NO and O2. And you can't change both of them at the same time. Because how would you know if we change both of them at the same time, then how would you know the increase in rate was because this was bigger or because this was bigger? So we can only compare runs where one of the variables remains the same. All right, so for example, if we look at the first two runs, 1 and 2, okay, this stays the same, right? This is the same. So if the reaction rate gets bigger, it's not because this went up, because this didn't go up. This stayed the same, but this went from 0.001 to 0.004. And the rate went up from 7.1 to 28.4. Okay, so you look at this and you say, okay, this goes up by 4, and this goes up by 4. What does that sound like? 4 raised to some power is equal to 4. 20.4 is 7.1 times 4. Okay, so in other words, 4 raised to some power is equal to 4. The concentration increases by 4, and the rate goes up by 4. So we know that order, that reaction order, with respect to oxygen, is 1. Okay? Now, let's compare runs 2 and 3. Okay, so now This stays the same. This is the same. So if the rate gets bigger, it's not because this went up. So this stays the same, and now this goes up. So the nitrogen oxide concentration goes up from 0.001 to 0.003, right? That's a factor of 3. This goes up by 3. What happens to the rate? It goes up from 28.4 to 255.6. That's a 9-fold increase. You divide 28.4 into 255.6, you get 9. So we think about this. So this goes up by 3, but this goes up by 9. So 3 raised to some power is equal to 9, right? So that reaction order comes out to be 2. Okay? So now we know that our rate of reaction, our equation, is rate constant, rate is equal to some constant K times the concentration of O2 times the concentration of NO squared. That's our rate law. Okay, so that's our rate law. So now we can, by plugging in data, we can figure out what the rate constant is. Okay, and so that's the next part of the problem. What would be the units, or what would, not the units, but what would be the rate constant? Okay, so we figured out the rate law. It's equal to some constant K times concentration of oxygen times concentration of NO squared. So all you got to do is take any of those data sets and plug them in, right? So I chose to use the first one. Okay, both concentrations were 0.0010, and our reaction rate was 7.1 moles per liter per second, right? So all you have to do is plug that in. So the rate, we knew the rate was 7.1 moles per liter per second. This is equal to some constant K times 0.0010 times 0.0010 squared. Okay, and this comes out to be 7.1 times 10 to the 9th liter squared per mole squared per second. We'll have some more to say about the units on that in a minute. All right, so let's carry this. Oh, and by the way, it wouldn't matter which data set you choose. We could have chosen the second data set. We could have plugged this in for a rate and these in for concentrations, and we would have got the same rate constant. Okay. So once you figure out the rate law and the rate constant, then you can figure out what the rate would be at different concentrations. So for example, what would be the rate of reaction when both concentrations are 0.0020? In other words, when oxygen was 0.0020 and nitrogen dioxide was 0.0020. That should be NO, actually. Okay, so suppose both concentrations were 0.0020. So now we plug in the data. We know the rate law and we know the rate constant. So 7.1 times 10 to the 9th times 0.0020 times 0.0020 squared is 56.8 moles per liter per second. Okay. So let's say something here about now the units on the rate constant. The units on the rate constant depend upon the overall order of the reaction. So in other words, what is the overall order? It's basically the sum of the reaction order, sum of the individual reaction orders. All right. So if it's first order, let's talk about first order first. All right. So first order rate is equal to k times some concentration of A raised to the first power. If you don't see a 1, it's implied. You don't have to write a power of 1. So if you don't see a 1, it's implied. Okay. So the units on the rate constant are basically whatever it takes to make the units cancel out. So in other words, you express a rate. A rate is a change in concentration over a change in time. Right? So concentration is moles per liter and time is seconds, right? So your rate is going to have units of moles per liter per second, right? So moles per liter per second is equal to K, and the brackets is concentration, right? So that's moles per liter, right? And so the moles and the liters will cancel, and that's going to give us units of 1 over seconds. So if you have a reaction where the overall order is 1, the units on the rate constant are simply going to be 1 over seconds. Okay. Now let's suppose we have second order. So the rate is equal to some constant K times a concentration squared. Right? So the rate is still going to be moles per liters per second. Okay. Change in concentration over change in time. But and a concentration is still going to be moles per liter. But now that concentration is squared. So the moles and the liters don't all cancel each other out. Okay. And read one more time, the units on K or whatever this works out to be after we cancel as many units as we can. So that to make the units the same on both sides, basically. So the units on K work out to be liters per mole per second. Okay. And then, if you have a third order reaction, where it could be something to the third power, or it could be where the sum, like we had in that previous example, where the sum of the reaction orders add to 3. As long as the overall order is 3, the rate is still going to be moles per liter per second. K is units on K is what we're trying to figure out, and concentration is moles per liter, except that's now cubed. Okay, that's now cubed. So some of the moles and the liters cancel, and this comes out, the units on K come out to be liters squared per mole squared per second. And if you go back and look at this problem that we worked, that had an overall third order reaction, right? Because this was to the first power. So our overall order here is 3, and this was our units on our rate constant, liters squared per mole squared per second. So that's a little bit of an introduction to kinetics. We'll stop here.